All right, so let's work this guy. We're going to find the slope and displacement at the midpoint of this beam. You'll notice that it's a simply supported beam. Pin at A, roller at B, and it's got this 5 kip load just off to the center. Now, even though we're finding the displacement, the slope at the center, you probably will expect that that is not the maximum displacement, and that this method wouldn't actually help us find that. If we have a particular point, in this case the midpoint, then this conjugate beam works great. If the problem were to find the maximum displacement and where it occurs, then you would probably have to use direct integration that we talked about previously and deal with all those issues. All right, so what do we do first in conjugate beam? We need to find the moment in the real beam. So I'm going to use this here, so I'm going to need to find some values. So I'm going to assume at A I have a positive shear acting up, and at B a positive shear, and I'm going to find those values. So how best to do that? I think I'll just sum moments at B. How about that? So I'll use right-hand rule for my sign convention, and we will sum moments at B and make sure it's in equilibrium. So about B, my 5 kip load creates what kind of moment? Positive or negative? Positive. So I have a force of 5 kips, and the distance from B to that force is 3 feet. And then I have my positive shear at A. That creates negative moment about B. And that has a moment arm of 12. So it looks like the shear at A is going to be 15 divided by 12. What is that, 1.25? So 1.25 kips is my shear at A. And then if you sum forces in the y direction, I'll assume up for my positive value. Then I should be able to find the shear at B. So I have the shear at A acting up, the shear at B acting down, and then my 5 kip force is also down. So I'll find the shear at B is negative 3.75. Does that make sense to everybody? Okay, so I'm going to use that information to draw my shear diagram. So I'll come over here and make a little template with the edges of my beam. And we know something's going to happen here at this 5 kip load, so I'll include that also. So we'll start with the construction of the shear diagram. Now I won't go into all the detail like we did in the past. I'll assume you can do that. But we do know that at A, I have a positive shear of 1.25. So there's my 1.25. And there's no load, so there's no change. And also, since the load is 0, the slope of the shear diagram is 0. So that should give me constant shear of 1.25 for the first 9 feet. And then as I go from the left side to the right side, my shear changes by the value of the load, which is negative 5. So it will drop down to negative 375. And again, the area under the load in the next section is 0, so no change. And since it's 0, 0 slope. So there's my shear diagram. Again, a pretty easy diagram. If you got this on the exam, you should be very happy. And then I'm going to use the shear diagram to construct the moment diagram. And this will have units of kip feet. Now we do know that the moment at A is 0, and the moment at B is 0. So we kind of know where we're going to start. We'll use our strategy. Hopefully we'll land there. So with the first 9 feet, we know the change in moment is the area under the shear diagram, which is 1.25 times 9, which is 11.25. So that gives us a positive value of 11.25. And you'll notice the shear value is constant and positive, so we have a constant positive slope. And then in the next section, over the last 3 feet, the area is, this is a negative area, this was a positive area. And this area will be 3 times 3.75. Hopefully that's 11.25, because when you subtract it, you get 0. That's good. And you'll also notice that I have a constant value. So that means I have a constant slope, and it's negative. So there's my moment diagram. So any questions about that? So now I'm going to construct my conjugate beam. So let's see. Remember our rules we talked about previously. An external pin in the real beam maps to what in the conjugate beam? An external pin. Nothing else is happening along the way, and then I got another external pin, a hinge, that maps as a hinge. So from a geometric point of view, it looks the same. So I still have a pin at A and a roller at B. So there's the conjugate geometry. What's the load? Well, remember what I like to do is I like to just put the diagram right on the beam. You'll also notice that it's going to be the moment divided by EI. So this now becomes 11.25, and that's kip feet divided by EI. Now, this is all positive moment, so which direction is a positive load? Up or down? Up. So this loading is going to be up. And we still have the same geometry. This is still going to be 9 feet and 3 feet. So now this is the problem you're working on. Everybody see that? So let's go ahead and use that particular location to think about how we're going to solve the problem. Remember, the problem wants the slope and displacement at the midpoint in the real beam. So slope in the real beam is what in the conjugate beam? Shear. And displacement in the real beam is what in the conjugate beam? Moment. So I just need to find the internal shear moment at the midpoint. So if I were to identify the midpoint, that's 6 feet. You now kind of get to think about whether when you cut the structure, do you want to work the left side or the right side? And I think in this particular case, there's a clear choice.
The left side. Yeah.
And the left side is going to be, I think, the easiest one. You just have a single triangular load. If you work the right side, you have a triangular section and then a trapezoidal section. That could be as many as 3 different little loads to keep track of. I think the left side's the way to go. So once you make that choice, then what you're going to need is the shear. Here's the positive shear at A. Here's the positive shear at B. I just want to find the shear at A. And then once I have that, I can cut the structure and find the internal values here. So my strategy first will be to find the shear at A, then draw this free body diagram and find the internal. Everybody see that? So let's do that. So I'm going to find the shear at A, I'm going to sum my forces or sum my moments about B. And to do that, I'm going to have to do something with this triangular load. The easiest way for me to do that, I think, is to break it up into two equivalent forces. One for this triangle over 9 feet and a second one for the triangle over 3 feet. Since I've already have a lot of stuff in there, I think I'm just going to redraw that to make it a little easier for you to see. So I'm going to come up here and let's see if I can do this in a nice way. So again, here's my positive shear at A and positive shear at B, and I'll just again kind of sketch in the shape of the load, and just to make it easier on myself, I'll indicate it as two triangles. So I'm going to have one force acting through the centroid of that triangle. I'll call that F1. And I'll have a second force acting through the smaller triangle. I'll call that F2. Now remember, I'm going to sum moments about B, so I need this distance. I'll call that D2, and then I'm going to need this distance, and I'll call that D1. So when I sum moments about B, I'll have F2 times D2, F1 times D1, and then balanced by this. So I just want to show you that conceptually. Now I'm going to figure out what those values are. So what is F1? What's the area of this part of the triangle? So that's 1/2 the base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. So I'm going to need your help for that. My Rain Man mathematics has run out. I can't do this anymore. So what's that? While you're doing that one, I'm going to go ahead and calculate F2. So again, that's going to be 1/2. To be this triangle. In that case, the base is 3 feet, and it's the same height, 11.25 kip feet, and that's again EI. So anybody get a value for the first one? 50 point what?
625.
625. Everybody else get that?
No.
Okay, so 50. I don't usually like to carry so many decimal places, but I will since that seems to be pretty accurate. And that's going to be kip feet squared divided by EI. And I guess this one's going to be a third of that. What's that number?
16.875.
Is that confirmed? 16.875? Cool. 16.875. And that again is going to be kip feet squared over EI. Okay, so what is going to be D1? That's the distance from B to the centroid. So that means I'm going to go 3 feet, and then from this point to the center, that's a third the distance, so a third of 9 is 3. 3 plus 3 should be 6. You guys see that? And then D2 will be 2/3 of the distance from this end, and 2/3 of 3 is 2. So now we can finally get around to solving the problem for the reaction. So now I'm going to sum moments about B and make sure it's in equilibrium. And now I have everything I need. So both F1 and F2 create what kind of moment about B? Positive or negative? Negative. So I'm going to have minus, I'll do F1, so that'll be 50.625 kip feet squared over EI. It's a lot to write down. Times, that was F1 times D1, and D1 is 6, minus F2, which is 16.875 kip feet squared over EI times D2, which is 2 feet. And then I have my shear, which is also negative moment about B, and it has a moment arm of 12 feet. So all that just to get the shear at A. Now, I'm thinking that since the forces are up, the shear at A probably is going to be down, so that means that it should be a negative value. So what do you guys get for that? I'm thinking like 27, 28.
28.125.
28.125. So that again will be kip feet divided by EI. And the negative sign I think is correct. That seems reasonable. I'm sorry, kip feet squared. Left off the square. Alright, now I can draw my free body diagram for the object. Remember, we're working the left-hand side. So let me draw that in. Looks like I'm going to run out of room here. I'm going to have to get a different one. So the shear at A is negative, which means it's actually down, and has this value of 28.125 kip feet squared over EI. This distance is 9 feet. Then I have the load, which is triangular, and it's still acting up. What do you think the value of this load is right here? Well, I know at 9 feet over, it is 11.25. So at 6 feet over, what should it be? Well, a similar triangle says 11.25 is to 9 as what is to 6? I think it's 7.5. 2/3 basically, right? Is that right? So this should be 7.5 kip feet divided by EI.
Shouldn't your length of the beam be 6 then? Underneath that?
It is. Thank you very much. It is actually 6. I just wrote it upside down. Let's make sure that 9 goes away. There we go. 6 feet. Thank you. So now internally, what I want to find is my shear. So this is the positive shear at the midpoint, and this is the positive moment at the midpoint. I need to find those two values. You know, also you can see that I need to find a new concentrated equivalent force. I'll just call it F3 since I've used 1 and 2. And what's F3 going to be equal to? Again, it's a triangle, so it's 1/2 the base, which we now know is 6, times the height, which is 7.5 kip feet over EI. And that looks like 22.5. So that's 22.5 kip feet squared divided by EI. And the distance will be 1/3 of the distance, or 2 feet. That's all I need. So there's a lot of work. So just a quick recap. We had to solve the original problem to get the moment, develop the conjugate beam, apply that as kind of a loading, and then now we cut it and we decided to work the left-hand side. The first step was to find the reaction at A, which we did. And then we applied that here. Now we've cut the structure and we're going to find these internal values. One I can squeeze in here pretty easily is to find the shear. To find the shear, I just simply sum forces in the y direction. I might be able to squeeze that in right here. So assuming up as my positive sign convention, I'll sum forces in the y direction. And when I do that, I've got the shear acting down. I've got my force F3 acting up, which I know is 22.5, and I've got this force also acting down, which is 28.125 kip-feet squared over EI. So it looks like the shear is equal to, it looks like it's going to be a really small negative value. Is that right? Let's see if I did this right. Down, down, up. Is that like 2.875? I'm guessing. What do you guys get? What's the difference between these two numbers right here?
5.625.
5.625, and that should be negative. No, I did that wrong. Did I? No, it's negative. Negative. So it's negative 5.625, and that's kip-feet squared over EI. So what do I do with that? Remember, the shear in the conjugate beam is really the what? The slope in the real beam. So I can come back now and compute the slope. So the slope is going to be that value minus 5.625 kip-feet squared, and I need to divide it by E and I. E for this problem is 30,000, and that's 30,000 kips per inch squared. I is 800 inches to the fourth, and I need to convert this feet squared. So there's 144 inches squared and a foot squared, and that 144, that's just 12 squared. This is going to be a really small number. I think I'm like 3 zeros or 4 zeros and a 7, I'm guessing. What do you guys get?
3.375 times 10 to the negative 5.
3 point what?
375.
Let's just say 3.8 times 10 to the minus 5. That's pretty small. And don't forget, that's going to be in radians. So we need to get the displacement I've run out of paper. I don't have any room to squeeze that in. Anybody have a piece of paper? Hopefully a piece of white paper with no lines on it. That would be really nice. I used to keep some extra here, but it seems to have vanished. Oh, thank you. So let's, I'll try to make this as seamless as possible. So, okay. Need to peel off my tape here. So let me slide that up a little bit. You guys still see that? Yeah. And I'll slide this underneath, and we'll try to finish it off. So I need to now find the moment here. So I'm going to sum my moments at the cut and make sure the whole thing's in equilibrium. So looking here at this free body diagram and some of the moments at the cut, my internal moment is positive. What's the moment of F3 about the cut? Positive or negative? It's going to be negative, right? So minus F3 and the distance is 2 feet. And then the reaction force is going to create positive or negative moment about the cut. Positive. And that's 28.125 kip feet cubed divided by EI. That's the force, and the distance is 6 feet. So from all that, I should be able to find the moment. F3 is 22, so it looks like the value is going to be negative, but I'll have to rely on you guys to tell me what it is. $100 and something? That was a wild guess. So it would be 28.125 times 6, 22.5 times 2. Subtract that.
213, 70.75.
213? Anybody else get that? Anyone? Bueller? Mr. No, what did you get?
I got 123.75.
123.75. Do I have more than one vote for that? Okay. Sorry, Mr. Streets. 123.75?
Yep.
And that's going to be kip feet cubed. So the minus sign makes sense because I'd expect the displacement to be negative, down. And we know that moment really maps to displacement. So our displacement at the midpoint should be equal to that. So it's going to be pretty small, 123.75 kip feet cubed. Now we just need to divide by EI and do some unit conversion. So just like previously, E is 30,000 kip per inch squared. Moment of inertia is 800 inches to the fourth. And cubic feet to inches, you have to have 12 cubed, which is 1,728 inches cubed and a foot cubed. So all that should have the units of inch. That's pretty small, whatever it is. I think it's less than 1. What'd you get?
Negative 0.00891.
0089, you got that? Now on the exam, I may help you a little bit by just asking you to leave the value with E and I. I may not give you a numerical value and ask you to do this. I could just say assume E and I is constant and not actually give you values of E and I. So the answer would just be this. Make sure you keep your units squared away. So again, pretty small displacement. Does that make sense? That the displacement is so small? Well, let's just glance back for a second. Remember the problem was a 12-foot beam with a 5,000-pound load on it. That's really not huge. And then this is a big beam made out of steel. 800 inches to fourth is a pretty big beam. So it's really not moving a whole lot. Okay. So any questions about that? I think that's doable, believe it or not, on the exam. Even though it took us 29 minutes to do it, there's a lot of chatter and discussion. But I think it's doable. Also, in review, if I don't require these additional final calculations. Also, it's quite possible in the exam to rig it so that these numbers come out a little cleaner and the calculations are a little smoother. Okay, so I'll stop it.